Assalamu alaikum and welcome to lecture number 9. Today we are going to discuss properties of the system. In the previous lectures we have completed the signals, their classification, operations on dependent and independent variable, and then we did some elementary signals. So this is second part of the course where we are going to discuss about the systems, right? So similar to the signals, uh, systems also have some different properties, or we can classify signals into different categories based on these properties. So in the previous lecture we defined the signal. We said anything, we define it as anything that anything is said to be system if it generates a signal, or anything that transmits a signal is a system, or anything that receives a signal is a system. Or we also say that anything that performs some operation on signal and producing a new signal is also a system. So we represented the signal system in the previous lecture by using, we said that we can represent it using the block diagram, using the mathematical equations, or using some operator. So in this lecture we'll discuss properties of the system. So let's start. These are the properties of the system that are system with or without memory, or we can also say we can classify system into those which have memory and those which are memoryless, or which are without memory, or stable and unstable system, causal and non-causal systems, invertible and non-invertible systems, and time-variant, time-invariant systems, and linear, non-linear systems. So the first property we are going to discuss is the system with and without memory. So we say a system is said to have memory if the present output depends on the present value of the input. It means the present output of the system does not depend on neither the future value of the input or the past value of the input. So if this is the case, then we say the system is without memory, or we also call it system a memoryless system. So memoryless systems can be discrete time systems, or they can also be continuous time systems. So examples of the discrete time system is shown here. So you see that what the system is performing here, it is scaling the input signal by a factor of 2, and it is also squaring the input signal and taking the difference of these, and then again squaring the difference. So if you look at this system, you can easily see that there is no shift involved, right? So if there is any shift involved, whether it's a positive, I mean, whether you're shifting the signal to the right or you're shifting the signal to the left, in that case we say the system, the output present value depends on future or past value of the input. So there's no shift involved, so that means there is no memory, right? So similarly, the case for the continuous time system is the resistor. So if you look at this equation, you can easily see that the present value of the output, which is current, depends on the present value of the input, which is voltage. So present value depends on present value of the output depends on the present value of the input. So that means this system is also memory-less system, or system without memory. For the system with memory case, we say if the present value of the output depends on past or future value of the input signal, right? So you understand, we represent input by X and we represent output by Y. So in case the input is continuous, then your input is x of t and output is y of t. For the discrete time case, input is discrete and output is also discrete, right? So inputs are x and outputs are y. So if you look at this equation here, so you can easily observe that the present value of the output yn depends on, you see, present value of the input, but there are also shift versions involved, right? So for example, if I add one more term and I say, okay, x of n, right, plus, for example, 2. So we say, you see, this represents a future term, that the present value of output not only depends on the present but also on the past, for example n minus 1, n minus 2, and also on the future, for example x of n plus 2. So such a system is called a system with memory. The example for the continuous time case is I of t, which is equal to integral of vt, and we take the limits of integration are from minus infinity up to t. So you can easily observe that because the present value of the output, which is I of t, is not only depend on the present value of the input, but also, you see, the past values, that is, we are integrating it from minus infinity up to t. So minus infinity up to t past values are also included. So that means this system is an example of a system with memory. I hope this gives you understanding and you can differentiate between the system with and without memory. The second property we are going to discuss, or second classification we are going to discuss, is the stability, is the stable and unstable, right? So we can also classify the system based on whether they are stable or they are unstable, right? So stability is defined as, we say, a system is said to be bounded input, bounded output stable if and only if every bounded input results into bounded output. It means if we have a bounded input, right, and the output is also bounded, in that case we say the system is stable. If the input is bounded and the output is not bounded, then we say the system is unbounded, or it is unstable, right? So the condition is that our input must be bounded. To check the system whether the system is stable or unstable, the first condition is that your input must be bounded, right? So if the input is bounded and output is also bounded, then we say a system is stable. And for such system, we say that output does not diverge if the input does not diverge, right? So for the bounded case, we say that the absolute value of the input signal, right, for the continuous time case x of t, so the absolute value of this must be bounded, right? That means it must be less than infinity, it must be finite. And at what instant of time? For all instant of time, right? That means from t running from minus infinity up to infinity, right, there should be no point where the input is unbounded. That means there should be no point where the input has infinite values. Input must have some finite values along all the t axis, that, right? Similarly, for the discrete time case, the absolute of xn should be less than or equal to bx, and bx should be less than, bx means bounded, right? So it should be bounded again, and this is also defined for the interval minus infinity to infinity, right? So that means there should be no instant of the x of t, x of n or x of t, where it reaches the infinity, right? So that means from minus infinity up to infinity, all the values of the signal should be finite. If this is the condition, then we say the input is bounded, right? So if input is bounded, then only then we can check whether the system is stable or unstable. If input is unbounded, then we cannot say, right, whether the system is stable or unstable. So the first condition is that we should have bounded input, and after that we go and check the output, right? So if the output, right, which is y of t for the continuous time case and y of n for the discrete time case, if these values are right for the continuous case, this is bounded. That means the value of it is less than infinity, right? Not at a particular instant of time, but from all time, that is from minus infinity up to infinity. There should be no instant of time where its value is infinite or unbounded, right? So again, the similar definition or arguments apply to the discrete time case also, right? So let's consider an example. So here, if you look at carefully, right, so the first system is doing what? You understand, the first system is just scaling the input signal. Okay, it's scaling it by a factor of 50 and adding some value which is 10, right? And if you look at the second system, so you see second system, it's integrating the whatever the input is, right? So it's an integrator system, so it's just integrates it, and it's the interval of integration is from minus infinity up to t. So if you look at the first one, you can easily tell that the first system is basically memoryless, because the present value of the input is the present value of the output depends on the present value of the input. If you look at the second case where it's integrating, so you can easily tell that this second system is basically an example of the system with memory, because the present value of the output not only depends on the present value of the input, but it also depends all the values from minus infinity up to t. So that means all the past values of the signal. So that means the second system is system with memory, right? Now we are going to test whether these two systems are stable or they are unstable, right? So let's see, the input is u of t. So for the first case, we say y of t equals to 50 times the input signal. Input signal is u of t, right? So you understand this is u of t plus 10. So do you think for there is any instant of time where this signal will result into infinity, right? So the first thing is whether the input signal is bounded. Input signal is u of t, so you understand u of t equals to 1 when t is equal to or greater than 1 when t is equal to or greater than 0, and 0 when t is less than 0. Okay, when t is less than 0. Okay, so that means at t equals to infinity, what will be the value of u of t? It will be 1. So that means if you go like by definition, so from all over the t, that is from minus infinity up to infinity, there is no point where u of t will be infinite, right? So it's either 1 or 0. So 50 times 1 will be 50 and 50 times 0 will be 0. So 50 plus 10 is 10, 50 plus 10 is 60, or 0 plus 10 is 10. So that means the y of t, which is output, can have only two values, whether it will be 60 or 10, and both are bounded. So first we check that the input signal is also bounded, and then we are checking that the output signal is also bounded. So that means this is an example of the system, uh, stable system, right? For the second case, uh, if we take this one, second system, so if I put the values in the second system, so you can easily tell, are you gonna tell? Okay, so in that case, y of t equals to integration, that is minus infinity, right, and up to t, and your x of t is u of tau, right, and d tau. So you understand, because u of t equals to 1 only when t is greater than 0. So that means I can write y of t equals to integration 0 to t, and this will be 1 d of t. You understand why I wrote 1? Because this is basically the input signal is step signal, so in step signal is 0 when t is less than 0. So that means it can have this. So that means integration of this will result into tau, and the values of tau are 0 to t, right? So if I put the values, so this is equal to t. Do you think this is an example of stable system or unstable system? So definitely unstable system, because we say for all values of t. Now if I replace t here with infinity, so y of infinity will be equal to infinity. So that means the although input signal is always bounded, it's right, but the output signal when t tends to infinity, it will be infinity. So that means this is an example of the unstable system, right? So that means integration, right, from minus infinity up to t. If this is the system, then it is, this system is an example of the unstable system. Okay, then we have another signal input, right? This is equal to this. So I hope you can go for it and you can plug the value of t equals t into u of t. So you can plug it here. Okay, so you can do this second example by yourself. Okay, so as far as the discrete time signal, this one is concerned, how about this one? Can you do it, or I should do it for you? Okay, for the second part, where x of t equals to sine squared t, you can test both of the systems shown on the previous slide. For this problem, I just give you some hint, right? So you assume that because to test whether the given system is stable or unstable, the important thing is the input signal must be a bounded nature. So when input signal is bounded, only then we can check whether the given system will be uh, stable, or in other words will produce bounded output, or the output is unbounded, right? So let's assume that the input is bounded and these are the values for the input, right? Now taking the absolute value of the both side, so because absolute value of the individual may be individual term will be greater than the overall absolute value, right? So for example, this is the equation that represents the input and output. I take absolute value of both the sides. Now I can write that y of n, absolute value of the y of n, which is output, and will be equal to will be less than or equal to absolute value of the individual terms. Here you understand why this is less than or equal to, because uh, if you take the absolute of individual, then you are just taking the positive sign, right? If I take the absolute of the overall, so for example here this term is for example negative, then it will be subtracted, right? And if I take absolute values for individual, then either they are positive or negative, it will result into positive, hence they will be added, right? So that's why in the first step they are equal, because this using this equation, this is the system representation, right? So this is your output and these are the input. If I take the absolute value of here and right input and again absolute value of the whole, they will be this will be represented by the equal sign. Whereas if I take the absolute value on the original individual term, in that case y of n may be equal to or maybe less than, so that's why I'm putting here. So that's x of n, then we have plus x of n minus 1 and absolute value of this, and then we again have plus I write here, right, x of n minus 2. Okay, I think somehow it looks like x2. Okay, and this whole is divided by 3. Okay, so I hope you understand why we write it in the inequality form, right? So we assume that x of n is less than or equal to mx, so replacing x of n by mx, so this is mx plus mx plus mx divided by 3, so mx, right? So mx plus mx and plus mx, it will result into 3mx divided by 3, so 3 cancels with 3, so that means y of n will be either less than or equal to mx. And because we have here defined that mx is basically a finite or bounded value, so that means this system is bibo stable. Okay, then the another property or classification of the system is based on whether the given system is causal or it's non-causal, right? So a system is said to be causal if the present value of the output signal depends only on the, right? So this is the present value of the output. So the present value of the output depends on the present or past value. So this is the present value and this is the past value, right? So if the present value of the input or output if the present value of the output depends on the present or past values of the input, then such a system is called the a causal system, right? So for example, shown here is a system, right? And what is the system doing here? I hope you can tell that it is just taking the average value, right? And how it's taking the average value, the present value, the present value of the input. This is the past 1 unit past value of the input, and this is 2 unit, right? So that means it is summing, right? It is summing and dividing by 3, so that means it's taking the average, right? So it's taking present and the past values are uh, involved here, so that means this system is basically an example of the causal system. Whereas in case of the non-causal system, the present value of the uh, output, right, will also will depend on one future value, one or more future value of the input, right? So if you look at this second system here, it can be easily observed that the present value, right, present value, which is y of n, depends on the present value, so that's fine. But here it is depending on the future value. So because this is depending on the future value of the input, then we call such a system as non-causal system, right? So if there's only one term that involves future value, right, so it will be a non-causal system, right? If there is one term or more than one term where the present value is depending on the future value, right, so we call such a system as a non-causal system. Then we come to another classification, that is invertible and non-invertible system. So a system is said to be invertible if the input of the system can be recovered from the output. So in case of invertible systems, distinct input leads to distinct output, right? So if a system is invertible, that means the distinct input will lead to a distinct output. So essential that there is one-to-one mapping between the input and output. So if a system is invertible, then its inverse exists, right? If a system is invertible, then its inverse exists. But if there's a system which is not invertible, then its inverse does not exist. So that's important for a system, right? That if it is invertible, then its inverse exists. If it is not invertible, then the inverse does not exist, right? So for a system to be invertible, distinct input leads to the distinct outputs, right? So if a system is invertible, then original system, right? For example, this is your input, that is let's talk about the continuous time case. So this is input, and this is, for example, your invertible system. I represent it by, for example, H, right? And right, so you give input to the invertible system and it produces some output which we represent by T. If this system is invertible, right, then the inverse exists, and if I put the inverse of this system in series with this, so let I represent invertible system by H inverse. In that case, whatever you give at input, you get it output, right? So that is, so I hope you understand. So for example, amplifier is an example of the invertible system. So for example, this is an amplifier, whatever you give it. So what does it do? It amplifies by factor of, for example, 5, right? So your output, for example, this is your output, so this is equal to 5 times the uh, x of t, right? So whatever you give at input, you get the amplified version by a factor of 5 of it, right? So what is it doing? If I write here, it's multiplying by a factor of 5, right? So what will be the inverse system? The inverse system will be the one that is dividing it by a factor of 5, right? So this is your input is x of t, and the output will be equal to 5 times x of t. Why? Because this system is multiplies the whatever input is by a factor of 5, so you get 5 times that, right? So what is the inverse of this system? Because it's this is multiplying it by a factor of 5, so inverse will be the one that will be dividing by 5. So if I divide 5xt by 5, I'll get x of t. Okay, so this is an example of invertible systems, right? So you understand, for a system to have inverse, it must be invertible, right? And when it is invertible when distinct input leads to distinct output. For example, we have a system that that does the square, right? So that means, for example, we have a system y of t, okay, and that's the output signal, and the system is basically x of t, right, and square. So that means it's a squaring system. Whatever you give it uh, at the input, the output equals to the square of that system, right? So for example, if you give it 5, right, the input is 5, so the output will be so for example, input is 5, so the output will be 5 square, right? So you get 5 square, which is uh, 25, right? So squaring system is not an invertible system. Why? Because here distinct input does not lead to distinct output. How? Because if I give it -5, the output will be, right, again -5 square is also 25, right? So you understand, although 5, right, and -5, they are two distinct inputs, but they result into same output, right? 5, so output is 25, -5, so output is again 25. So that means, although the inputs are distinct, right, the inputs are distinct, okay, I just encircle here, the inputs are distinct for the case of squaring system, but the outputs are not distinct. So squaring system is an example of non-invertible systems, right? And you understand, it is must for a system to be invertible. If for a system to have inverse, it is must that it should be it is invertible. If it is invertible, then inverse system exists. And when you cascade the inverse system, like I have shown here with the original system, whatever you give it at input, you get the same at the output, because the two systems, they are inverse. So whatever the system does here, okay, with the signal, the reverse is done here, and so that means you get whatever at input here, you get the same out of the same thing at the output. So another system is identity system, right, which is defined as a system whose output is equal to the input for all possible inputs, is an identity system, right? So for an identity system, whatever you give it at input, you have the same at the output, right? So the invertible systems are very important, right, in communication and different areas, right? So for example, you can say that you encode, you have input, for example, some very important information, and you just use some code to encode this information. Now it is right. So after doing this operation or encoding operation, you get something y of t, and then you send it over long distance at receiver. And if you have the inverse system, then you just decode it, right, and you get the original signal whatever you sent. So it has many important applications. So this is exactly what I have shown you on the previous slide. Okay, so this one, for example, your output, so you can easily, if a system does this, right, so what will be the operation of the inverse system? So definitely this system is multiplying by a factor of 3 to whatever input comes, right? So and then adding, so the inverse system should be dividing and subtracting by 5, right? So uh, you get the original, the whatever it input is, you get it output, right? So that's about the invertible systems. In this example we have already done, right? Because in case of squaring, distinct input does not produce distinct output. Okay, the next classification is the time variance and time invariance, right? So how do we define the time invariance, right? So it is defined as if a time shift in the input signal results in identical time shift in the output signal, then the system is said to be time invariant, right? So I can explain it. So we can say that the characteristics of the time invariant system does not change with time. For example, you check, you have different system. For example, you have a tube light, it gives you some light, right? So if you give it to 20 volt today and it gives you some light, and after 2 days again you give it to 20 volt, okay, and if it gives you the same amount of lux means the light, right, luminance, so that means this system is time invariant. But if it changes, for example, you have a fan and you give it, you turn it on today, you give it the its required power, you get some air, right? The rotations, for example, some amount, right? So if the next day it gives you again the same, so that means this is an example of time invariant system. But if you give it today some power and it gives you any electrical system, right? So if for example, if we say it's the, if the light of the tube light changes with time, that means it's a time varying thing. But if it doesn't change with time, it stays the same, then you say it's a time invariant. Okay, so how to check whether a given system is time varying or it is time invariant, right? So it's a straight away two-step procedure, right, as shown by the block diagram here. So what you do, you give it, you have the input signal x of t, okay, and you shift the input signal by amount of t naught, okay, and so x of t now results into x of t minus t naught, okay, and then you apply some system, right, as shown by the h here, so you get some output here, okay. Again, you have the same system. Now what you do, you give the input to the system and you get some output, okay, here, and then you shift the output by the same amount. Now if y0 equals to y1, right, this is your y1, y1 of t, okay, if y1 of t equals to y0 of t, then you say system is time invariant, okay. So it's a two-step procedure. In step 1 you shift the signal by some amount t naught and then you find the output, okay, and the step 2, using the signal you find the output and then you shift the output by amount of t naught. If this output equals to this output, then we say the system is time invariant. But in case they are not equal, then the we say system is time varying. That means system's properties are changing with time, right? So similar thing is shown here using the equation. So you say, okay, input, shift the input by n naught and find the output, right, and then find the output and then shift the output by n naught, okay. So I think both are same. Okay, so if this output and this output, if they are same, then we say it's a time invariant, otherwise we say it's a time varying system. So to elaborate the idea of how the idea of finding the property of the system, that is time invariance, let's take some examples. So here we have an example, and by looking at the equation, I guess you understand what the system is doing. So again, it's a squaring system. Y of n equals to x square n. So this is your output signal, and this is your input, and the equation says that the system is doing is just taking the square of whatever you give it at input. So you want to check whether this system is time varying or it's time invariant, right? So this first step is that you find the you delay the input and then find the output. So if we have input equals to x, if I delay it, input is x of n, so if I delay it, so that's x of n, right? So what I do, I delay it, not delay it, shift it by amount of uh, n naught, right? So what I get x of n minus n naught, and now I apply the system, right? So let I represent it by h. Okay, so what is the system doing here? So you understand, it's taking the square of the whatever is input. So what should I get here? I should get here square of the system, so that will be x square, right, n minus n naught. So this is I get using the first step. Now in the second step, how we proceed. So for the second step, we take the input and we find the output. So this is my input, and I have system, right, that is h, and I find the output, right? So the output here will be, because what is the system doing? System is taking the square of the input, so this is x of n. So what will be the output here? It will be something like x square n. Okay, so this is output here. Then the next step is that I shift it by amount of s naught, s n naught, right? So this is what I'm doing, shifting here. So what I, right, so after shift, right, what I get, I get x square, right, this is x square n minus n naught. Okay, so the output I get here, you check. Okay, so this is the output I get here in the second step, and this is the output I get in the first step, or step A and step B. If they are similar, not similar, in fact if they are same, then we say the system is time invariant. But if they are varying, or if they are not same, right, you get different answer in the step A than you get in the step B. That means this system is time varying, right? So for example, let me do this another example so you understand, uh, right? If I, this is the n into xn, right? So uh, let's take this example. So for this example, what will be the what is the system doing here? System is multiplying n with whatever you give it at input, right? So in the first step here, right, at this point I will get or let me draw again. Okay, I redraw. So I just have x of n, right? I'm just talking about this example, right? So I have x of n, and after amount of shift by s and naught, I get x of n minus n naught. Okay, and then I apply the system, right? This goes to system H. Okay, and what is the system doing here? The system is uh, what is the system doing here? So it's multiplying by n. So I should get here n into x of n minus n naught, right? So this is n minus n naught. Okay, now in the second step, what I do, I apply the system. Okay, so this is my input. Okay, and this is the system H, and I get, because system is multiplying, you see, by n, so I should get something n into x of n minus n naught. Okay, now if I delay this by, not delay, if I shift this by amount of n naught, right? So what should I get? I should get because this is n, so n is shift. Okay, so n minus n naught, because, right, and this is x n minus n naught. Okay, so this is my output here. Okay, and this is my output in the first step. So you clearly see that this output is not equal to this one, hence it is time variant or time varying system. Okay, so I hope you got the idea and you understand how you can do. So it's a straightforward two-step procedure. In the first step, you delay the input and find the output. Okay, and in the second step, you find the output and not, sorry, delay, right? Again, I repeat, in the first step, you shift the input and you find the output. Okay, then again you find the output and then you shift the output, right? So if the answer you get in the first step here and the second step here, if both the answer are same, that means the system is time invariant. But if you get different answers, then the system is time varying, right? So the first example which we did here, that is the square law system or the square law device, right? So we proved that it is a time invariant. But in case of the second system, which is represented here by this equation, and you understand y of n is the system is what the system is doing. It's multiplying n with whatever input you give. So this system is an example of time varying system, right? So there's another example, y of t equals to sine of xt, right? So whatever you give it at input, the system is taking the sine of that input, right? Sine wave, sinusoidal, right? So this is a homework for you. You can just try it at your home and you check whether it's a time varying or it's a this system, right? So or it's a time invariant system, right? So that's all for today. See you in the next class. Allah Hafiz.